All right, welcome everybody. We are dealing with the last little bit of new learning for this unit, for our unit in probability. Uh, we are talking about the binomial model, but in this case, what happens with a large number of trials in a binomial situation? So the ones that we were calculating the other day had small numbers of trials, like 6 or 5 or 10 or 15 or something like that. They were all very small amounts, easy to calculate. In fact, if you had to do the binomial, if you were doing it by hand using the 5 choose 3, even if we had to do like p of x is less than 3, it's not a terribly difficult thing to do, right? Because you have uh, you would only have to do this part 3 times, okay, for the 3 different numbers. 5 choose 2, a p, I'm just writing as a note, a probability times 5 minus 2, right? Writing this all down is not a problem. We could do it that way, not a problem for your calculator. The problem happens when we have large numbers of trials. Like say we had some kind of situation where we had to do p of x is less than or equal to 512, right? What if we had to write this 512 times? Even your calculator has a hard time calculating a binomial probability that large, okay? So the 84 is kind of, you might be able to deal with it, but if you have an 83, if you try to do something like that, it'll pause for like 5 seconds because it's like thinking, because there's so many calculations happening. Because look, it's doing this 512 times. Fortunately for us, when we have such a large number of trials, we can, instead of doing this with a binomial model, we can model it with a normal model. So, as long as this condition holds, the success-fail condition holds, we can use the normal model to approximate the binomial probabilities. And so what's the success-fail condition? Get used to this one because you're going to see it a lot in the next 4 months. The success-fail condition states that a binomial model is approximately normal if we can expect at least 10 successes and 10 failures. So if I took my probability of success and multiplied it by the number of trials, and that was more than 10, and my probability of failure times the number of trials, and that was bigger than 10, that means it's big enough to be approximated with the normal model, okay? So just as an example, let's say I'm doing 100 trials. I'm flipping a coin 100 times, and I'm going to see what's the probability of getting 65 heads, okay? My trials is 100. My P is 50%, so is this big enough? 100 times 0.5 is 50, which is greater than 10, so that checks out. And 100 fails times 0.5, that is also bigger than 10 because that's 50, and that's bigger than 10, so that checks out. If I wanted to model flipping 100 coins with a binomial model, I could flip it 100 times and it would be big enough. Technically speaking, I could flip it 20 times and it's big enough. And it would be technically big enough to do it, okay? So this success-failure condition just states it needs to be big enough that we can expect to get 10 successes and 10 failures, okay? So let's look at an example. We're going to skip this part, but what would it say? When we use the normal model to approximate the binomial model, we're using what's called a continuous random variable to approximate a discrete random variable. And everything that we've been doing with the binomial and the geometric have been discrete random variables, single pieces. Normal, when we use the normal model, that's a continuous random variable. Which means we no longer calculate the probability that the random variable equals a particular value, right? It's no longer x equals 3, but only that it lies between two values. And one thing that you're going to notice about this is that it is remarkably similar to what we did in Unit 1 when we were finding z-scores, okay? Because we're going to use a normal model. We're going to find a point on that normal model, and then we're going to find the area shaded in one of the directions. And you guessed it, that means we're using the normal CDF command in order to find probabilities. So let's look at an example. Back to our spam example. 91% of email messages are spam. Boom. Recently, I noticed that my spam filter was only okaying 151 of 1,422 emails, classifying the rest of the emails as junk mail. With that particular 151 out of 142, should I worry that my filter is too aggressive? Is it filtering out too many emails? Okay. So we can use the probability to determine if this is too aggressive, right? If it's a 91% rate of spam, if this is not close enough to a certain probability, it might be, if the probability of this happening, is too low, then this means that it might be too aggressive. So what we're looking for is what's the probability that no more than 151 out of 1,422 emails is a real message. So we're looking for 151 and smaller. So let's first check some things here. There's a problem. What's the probability that no more than 151 out of 1,422 emails are real messages? Let's check our conditions. Is this a binomial situation, first of all? And the answer to that question is yes, it is a binomial situation. It is because I have a fixed number of trials, 1422. What's the probability that 151 out of 1422 are real messages? Yes, this is a binomial situation. Yes, family, that's there. Can we approximate the normal? So, are they, ignore this. No. So the question is, can I expect successes and failures to produce 10 of each? And nope, I don't actually put the numbers in there. So let's see here. I'm expecting 151 successes. And how many failures is that? 1422 minus 151. That's 1,271 fails. Did I get 10 of each? Absolutely I did. So my conditions are met. I can use a normal model to approximate this. So what we need to do is find the z-score for this probability. So let's just really quickly review what the heck is a z-score. Remember, we had a normal model. The mean was 0. And then we had 3 standard deviations out. 1, 2, 3 standard deviations out. 1, 2, 3 standard deviations out. These were negatives over here. The z-score, we'll write it up here. Z-score was the number of standard deviations away from the mean. And we need to calculate what that is. And we had a formula for that. It was z equals data minus mean over standard deviation. So we have our data here, right? Z equals 150. Let's do this 151 out of 1422. Let's do that as a decimal. So 0.106. That's our 151 out of 1422. That's the 0.106. We need a mean and we need a standard deviation. Well, we can find those things. We don't have them now, but we can find them, and we can find them fairly easily because the mean of a binomial situation you will remember, is n times p. So my total number of trials, 1422 times the probability of success. In this case, we're talking real messages, so that's 0.09, and that is my mean. So that's 127.98. I think I lied to you a moment ago. We want this to be 151. Okay, so my mean is 127.98. And then what's my standard deviation? Standard deviation for a binomial model is the square root of NPQ. So that's the square root of 1422 times 0.09 times 0.91. So square root, I'm doing that now, 1422 times 0.09 times 0.91. That is 10.79. So 10.79 is my standard deviation. Now I need to calculate my z-score. 151 minus 129.98 divided by 10.97. We get 1.91, which, by the way, is about right here. And then we ask ourselves, what's the probability that no more than 151 emails are real messages? So at least means above, no more means below. So we need to find this probability down here. And if you recall, that means we're using the normal CDF command. Normal CDF. We're using a very small number over here, -10, and then we're going to go up to 1.91, and that will be the probability. Oops, I did a wrong thing. Normal CDF, -10 and 1.91, paste. This is a 0.972. So what's the probability that no more than 151 of 1422 emails are real messages? There is a 97.2% chance that that's going to happen. So is my email filter too aggressive? Nope. It's pretty dead on. It's catching, there's a high probability that that's going to happen with 90%, with a 91% spam rate. So my spam filter is doing pretty good. Okay, so there's our example. It's a pretty long one, right? Because we got to remember a bunch of stuff from chapter 1. We got to remember how to calculate z-scores, and we got to remember to do means and standard deviations of a binomial model. So there's a lot of pieces to this, okay? So we're going to do a lot of practice with this one, as well as continuing with our binomial model. That's going to be our all right. Thank you. We'll see you later.